The reason why I was interested in self-normalization, in machine learning, the way I found out about problems in machine learning was by looking at Google. I used to get notices when my papers were being cited, and I, so that's how I found out that this was being used in machine learning. In particular, what I'm going to present today has been used in one of the most used papers by Abase, Yakitori, and Sebaski on linear stochastic bandits. The paper has about 2,000 citations in Google. And so they use one of the inequalities I would show you in obtaining their bounds and confidence interval. And Caroline is going to talk more about that. But I'm going to focus on proving the inequality and other results. Okay, so let us get started. Okay, so we already went through some background on self-normalization. Now, the main tool that we use for self-normalization is what we call pseudo-maximization. And it's a continuation of the method of mixtures, and I will explain what the difference between the two is. Then I'm going to show a Gaussian bound. Or remember, we have A and B are variables, and they satisfy a canonical condition. So I'm going to show a Gaussian bound on this quantity. Then, in order to prove this, I need to get a bound on the expectation of A over B. And so I'm going to go through that, and then I will briefly review the matrix value self-normalization, which is what is used in the machine learning literature. I might do this, but it's not necessary. The only difference here is that you can replace the expected value of P by the expected absolute value of A to the P to the 2 over P. And the tail bound, it looks very much like the Gaussian bound. But this one already has that element. Now, I will talk about boundary crossing problems, which, in the abstract to this course, we have discussed the log theta logarithm, Kolmogorov's LIL. So by using the method of pseudo-maximization, we are able to extend the Kolmogorov's LIL to the case of martingales and to the case of sums of conditional symmetric values. So that will be explained. Okay, so now let's review the canonical assumption. So suppose that we have two variables, A and B, with B bigger than 0. That satisfies this condition. And the condition we call for all real lambda, which is the one that I will use mostly in this talk, or for all lambda bigger than 0, or lambda between 0 and a fixed lambda. So each one of them gives you a different inequality. So each one has its own problem. So this is supposed, so basically this is the super martingale. Well, we assume that this is true for all lambda in the beginning. And if you have that, then we have a lot of inequalities that derive from that. Now, let me see. One second. Let me try to show you examples of where this is satisfied. Because, if you just came in today. Okay, so it might be, it might be coming out of the blue. But remember, we have two variables. One is A. This would be what A is. There should be a lambda here, we took lambda A minus lambda square over 2, then then this quantity, that's B squared. And where x sub I we have is the martingale different sequence. So these are martingale different sequences. And this is a combination of the conditional variance of the martingale plus its sum of squares. So that's an example where the canonical assumption that I showed is satisfied. So in particular, all the results that I will present apply to martingales, where you replace A by the sum of x sub I and B by this sum. Okay, any questions? So this is for discrete martingales. And we also have, you know, as I said, we can then apply the tools to obtain an inequality that looks very much like the Gaussian tail. Okay, so by using self-normalization, you can get Gaussian tails. And so I just wanted to show an example of where the canonical assumption is obtained. Another place where you can use is continuous time martingales. So for continuous time martingales, A would be the martingale, MT, and B would be the quadratic variation. B squared, the quadratic variation. Okay. So that's just that's a little bit of a review of what I did before, just to set up the motivation for going through all these inequalities. Okay. Okay. So this is the canonical assumption. So in the case of martingales, you let this to be the martingale, continuous martingales, and this is the quadratic variation of the martingale. Then that is satisfied for all continuous martingales. Okay, so now the ideal inequality. So you think if you have this condition satisfied, if this condition is satisfied, then one can hope to obtain an inequality of this type, where what you have is the case of martingales. A would be empty, B would be square is the quadratic variation, so this is the square root of the quadratic variation. And by using Chebyshev's inequality, you have that this is less than or equal. This is equal to probability of A to B. Probability of A squared. Okay, so this is exactly this. And then by using Markov's inequality or Chebyshev's, you get this bound. And if we look at the maximizer, if I replace lambda by the maximizer A over B squared, then because of the pseudo maximization, this is going to be less than or equal to 1. And we get the bound into the minus x squared over 2. I don't know if you're familiar with Chernov's bound. This is sort of the type of thing, the best type of that you can hold to for sums of independent bounded variables. Now, what we were trying to do was extend the results for sums of independent variables to the case of martingales over their square root of the quadratic variation. So it's sort of like self-normalization. So now, since A over B squared, yes.
A over B squared in general is random, right?
Yes, that's what's going
that's
to
coming
be.
up. Sorry.
So A over B squared, good, thank you. So since A over B squared is random, so then we need what we do. So that motivates the whole work. So we need an alternative method for dealing with the maximization, okay? So, and the approach we use is called pseudo maximization. which is basically a continuation of the method of mixtures, and I will explain how this works. So suppose that you have gamma to be a measurable set, and you construct a finite probability measure lambda with distribution F, independent of A and B. This is the most general situation that we would treat. But if you want, you can think of F as 1, because this is the cumulative distribution function of F up to plus infinity, which is always 1. So if you have a density function, this expectation by assumption is going to be less than or equal to 1, right? That's the canonical assumption. Now, what we do is we multiply. So we want to find the value that maximizes this quantity. Now, since A over B squared is random most of the time, then we want to find a way to retrieve the maximum of some sort of maximum, which we call the pseudo maximizer. And the idea is to multiply this by a density, df. Okay, so we multiply this by df, and by using, so I integrate over df of lambda d lambda, I integrate over the density, and so that's what this is. The integral over the density. Then I take the integral, outside integral with respect to df of lambda. No, yes, df of lambda. So I'm multiplying with respect to density on lambda. Is that clear? And then I integrate, and I use Fubini's theorem to write it this way. Okay? Questions? Please stop me if there's a question. Now, the canonical assumption tells me that this is going to be less than or equal to 1. And so I'm going to use that in the subsequent discussion. So when we assume that you have a probability measure, this is then 1. And I want to find, what we do is we find a density that will capture almost the maximum. So the density that we use goes very flat. So if you want to think about it, if the density is flat, then the maximum will be picked up by the interval. That's the idea. So the maximum value, at the lambda, so there's a regime. So to be effective as possible, the F chosen would be as uniform as possible as to include the value of e to the minus lambda, a minus lambda square b square over 2. The idea is that if lambda is a random number, a random variable, the maximizer is a random variable. What you want the density to be very flat, so that when there is the maximum is contained somewhere in the interval. Okay. So you don't have to have a density. All you need is a measure, finite measure, and that's important because finite measure that vanishes in infinity. It's important for the law of literal logarithm. Okay. Now, so let's prove this inequality. So this is from my paper with Michael Glass and TLI. So the idea is, so we have under the assumption, the canonical assumption, you get that the probability of A over the square root of B squared, EB squared, you get a handle on the tail probability of this. Remember, the ideal inequality would be with this equal to 0. But you cannot get that. That's impossible because of the structure in the problem is random. But if you have this quantity, the expected value of B quantity squared, and you plug it in, you get something similar to what you were looking at, except for constant square root of 2 e to the minus x squared over 4. Okay? So this is close to the opening. Okay. So is there any question about this? From this, you can get LP moments and you can get some large deviations for self-normalized processes. So if you're interested in those, this allows you to get self-normalized results for martingales. Now, if you're interested in heavy tail, this is particularly helpful because you can do self-normalization for heavy tails, martingales with heavy tails. And that's something that Kim and Chow, my co-author on the book on self-normalization, that's something that he has done recently. Okay, so in order to obtain the exponential inequality that I showed here, what we do is we are going to assume the canonical assumption holds for A and B, and then we are going to show how to get this out. So for any y bigger than 0, and assuming the canonical assumption for all lambda real, then we have this expectation less than or equal. And we are going to use this inequality to prove the exponential inequality. Now, why is any real number? Okay, so now, I have the proof of the inequality is just 1, 2, I don't know, this is a stretched second line, and then a third line. So it's 3 lines, like most of the proofs here. Okay, so once you find it, it's 3. So anyway, so we have the canonical assumption, and this expectation is less than or equal than 1. So I have 1 bigger than or equal than this expectation, and then I integrate with respect to a Gaussian density. Okay, with mean 0 and variance 1 over y. So this is a Gaussian density. Usually you have 1 over the square root of 2 pi, then the variance sigma would be 1 over y. And so that's how it works. Okay, so then this will be bigger than or equal than this quantity because I integrated on both sides by the density of the Gaussian. So the left-hand side is 1, and on the right-hand side I have this. Then I use Fubini's theorem. Make this integral inside. And then what I do is I complete the squares. So the interesting thing is that once you take the expectation outside the integral, you can think of these as constants because they are like frozen. The expectation comes outside the integral. So if you pick, we have picked the density e to the minus lambda square y square over 2. For that density, we want to complete the squares where A and B are fixed. And then once doing that, we get the inequality that we're looking for as follows. So I want to complete a density. So you see, if I have minus lambda A, so you look at this quadratic form. So I have lambda squared minus 2a over b squared plus y squared plus a squared over b squared plus y squared over 2. Now, this is basically lambda minus a over b squared y squared. What is squared? That's what this is. Okay? So in this case, what I do is, if you want to think about it, as lambda changes, this is basically like the density of Gauss. Lambda minus a over b squared. So what we have is the density of the Gauss. Okay? And by adding and subtracting, we can go from this one, and Fubini's, and then we add and subtract, and we end up with this. Okay, questions? So now we are integrating, we do a change of measure. So the new measure is normal. Lambda is normal with mean A over B squared plus Y squared, and the area is 1 over B squared plus Y squared. So that's actually, this should be A over the square root of B squared plus Y squared. Because when I factor this out, I have lambda minus A over the square root of B squared plus Y squared squared. So what I have is e to the minus this quantity. And then I have over 2 times something over 2. Okay. So this quantity takes the case, it's related to the variance of your variable. So it's 1 over the variance. So by completing things, I make, the Gaussian density has variance at the bottom and square root of 2 pi. And here I have 1 over the sigma, 1 of the standard deviation, and the square root of 2 pi. So this very much looks like a normal density. Okay? So when you integrate over that, using the change of measure, lambda is normal between A over the square root of B squared plus Y squared. I get what? What do I get when I integrate? So this quantity, okay, so let me think. I have to show, oh, okay, so I add and subtract. So in order to come up with this formula, okay, to this entire formula, I added and subtracted this quantity. That's what made the quadratic form. So then I end up with this, and when I integrate, it integrates to 1, so I have this expectation. So that's the full proof of the inequality. Okay, any questions? So this is the main inequality, and it is used, it was used by Abbasi, Takidoki, and Stebatsky. So there are 3 authors. And as I said, it's a very influential paper in machine learning in this theory of linear stochastic bandits. And Shaolin is going to talk about that paper and the application of this inequality. Okay, so let's prove now the exponential bound that I said. So far we have proved this inequality. If we use Cauchy-Schwarz, this is going to then be, I multiply, so I start here, and I multiply and divide by the appropriate quantity. So I multiply and divide by the square root of the 4th root of B squared plus Y squared, multiply and divide, and times Y over the square root of B squared plus the 4th root. Okay, so it's going to be Y over the 4th root. And then when I use Chebyshev's inequality, I can get this. So it's Y squared over 4th root of B squared plus Y squared. Multiply by that and divide this. And then I use Chebyshev's inequality, Cauchy-Schwarz inequality, I'm sorry, to end up with this. This product, the square root of this quantity plus this times this quantity. Now, I know from what's above, what I proved before, I know that this is less than 1. So that gives me this inequality. Okay, because this is less than or equal to 1. So I have the square root of expected square root of B squared plus Y squared over Y squared. And then the next step, so this is like step 1. There are 2 more steps. One is since the square root function is concave, I can write this as the okay, good. So I have this. So since b is non-negative and the square root is concave, then I can have this bound. So I take b over y plus 1. So this expectation, the square root is bounded by e of b over y plus 1. Now, if I set b y equal to eb, it's constant. The inequality is true for every y, which is bigger than 0, and this is such a y. Then I end up with this inequality. Now, if I, as I said, if I let y equal to eb, then I have b squared plus eb squared. Okay, when I look at this, I have eb over eb. Okay, it's b over eb plus 1, which is the square root. So that's how this happened. If I use Markov's inequality, then I have that this quantity is less than or equal than is equal to probability of a squared over 4b squared eb squared b bigger than or equal than x over 4. And then I use Markov's inequality and I end up with this. Okay, using the inequality that I just put. So this is maybe a 8-line proof. Okay, and it's the main result. I mean, it's a Gaussian inequality that can be used to do large deviations for martingales, which I understand are related to queuing processes or Markov chains, the Markov chains. So this can give you an exponential inequality, Gaussian exponential inequality for Markov chains. Now, in the application to linear bandits, they use a matrix version, which was published in 2009 in a paper in stochastic processes and its applications. So let me show you what the version is, the multivariate version, the matrix normalized process. So we can then extend the canonical assumption to the setting of random vector A and symmetric positive definite matrix C. This expectation is going to be less than or equal than 1. Yes.
The previous part you were saying that the pseudo maximization that you want to be as flat as possible. But then eventually we ended up picking Gaussian.
Oh, yes. So the example on the low logarithm is the one that uses the very slow density. This one uses the Gaussian. So you can use different densities to get different inequalities, and in different applications require different densities. Okay. So this expectation is of course bounded. Now, so this is the following two lemmas are extensions of the corresponding results in lecture 6, and more examples appear in my book with Kim Chow and Lai on self-normalization. Okay, so here are the examples. So this is our assumption on the new canonical assumption for vector value A. So we have, if you have a continuous square integral martingale taking values in Rd with m of 0 equal to 0, then e to the theta p minus mt minus theta 2 transpose theta transpose minus theta transport, the variation of MP theta over 2 is a super martingale, and therefore this expectation is less than or equal to. So you can deal with vector value processes. Now, for those of you who like heavy tails, this is a result on that allows us to get exponential inequalities, sub-Gaussian exponential inequalities, even in the case where you have infinite variables. And so, okay, so suppose we have a sequence of sigma fields. So we have a sequence d sub I, which is adapted to an increasing sequence of sigma fields sub I, and we assume that the d sub i's are conditionally symmetric. That means that the conditional distribution of di given phi minus 1 is equal to the conditional distribution of minus di given phi minus 1. Then this is satisfied. So the canonical assumption is satisfied. This requires a long proof. So this is one of those rare cases where you need a long proof. And the special case of this, if you're not familiar with conditional symmetric variables, is the case of symmetric independent variables. So you have independent symmetric variables, this condition is satisfied. So this inequality is true for all symmetric variables, independent symmetric. They don't have to be identical. So in particular, it goes for Cauchy random or stable random, symmetric stable. So this tells me that the inequality, this inequality, is going to hold even when I take the sum of the Cauchy variables over the square root of the sum of the squares times the first moment. I mean, actually, no. I do not need to worry about moments because the Cauchy doesn't satisfy any moments. In that case, what I do is the inequality is true for all y bigger than 2. So I guess if you have Cauchy, then you don't assume that they have moments. And you see this inequality holds for every y bigger than 0. So you can get different inequalities that are satisfied for sums of Cauchy variables. Any questions? Any questions? So, okay. So we're here. And so the dilemma was that under the canonical assumption, we have this for every y bigger than 0. And in the vector, when we have a random vector A and a symmetric positive matrix C, C is the one that takes the base for Y. Okay, then no, C is the quantity that takes the place for B squared. Okay, then we have this, and using the same technique that I showed before, we can end up with this. So it's the same proof, except we have to do multiple integration. So here are the details, but I don't want to bore you with them. It's just the same proof follows. You have to just be careful. You have my matrices and vectors. And then use the same technique. So, okay, now, okay, so the paper of Abashi and Jackie Dorley and Spivak on linear bandits has this as one of its remarks. It says the improvement, so they are talking about improving the known results for linear bandits. And the improvement comes from the construction of smaller confidence intervals. For their construction, they used a novel tail inequality for vector valued martingales. And the inequality is precisely this one. So they use this inequality as as the foundation of their result. So this comes directly from their abstract. So they are saying we're using self-normalization in order to obtain our results. The main innovation is the self-normalized inequality. And unfortunately, in their paper, the reference to our work is hidden. It appears in an appendix, and that is hard to find. It's not so that I guess no, this paper has 1,800 citations roughly, and our paper has about maybe 350. So we could have maybe a few more citations. But they did extra work, and Calvin is going to show. This was just the key inequality, but you know, it's full of new ideas that they in machine learning. Now, let me see. So I don't think I can go over this because it's getting late. But the techniques used for this Gaussian bound, which is this quantity. Here we are looking at for p, so we have expected a to the p finite for any p bigger than or equal than 1. So we are changing EB squared by this quantity. The quantity b squared by this quantity. And then you get a very nice Gaussian inequality. So this was published in 2009 with Woodon Pine, and as I said, it has found applications in moderate deviations for self-normalized martingale. And depending on what p you pick, you get different limits. Now, if you're familiar with the tail bounds, two-sided tail bounds for the Gaussian variable, these are very close to the two-sided bounds. So you're really getting a lot out of this simple idea. Does anybody want to see the proof of this? It's not 3 lines. So maybe we might come back to it later if there's need. Anyway, so let me just go through it quickly. The technique is the same, except that we include an arbitrary set G. So you can prove this inequality with constraints. So you're constraining your variables to be on a given set. And then using the same technique, Chebyshev's, folders, you can come up with all these things, including you have to carry the set. And then that, in the end, gives you this. And then the examples I just showed you. So here we have a martingale up to a stopping time. And you can use these. So Pan et al. Applied the theorems of De La Peña and Pan to construct self-normalized primary type with moderate deviations for self-normalized martingales. If you're interested in that topic, then you can look at the reference number 8 in this flowchart. Okay, so now one of the main attractions for the course was the extension of Kolmogorov's law of iterated logarithm to the case of self-normalization. Now, let me set the stage. Why is this important? So, when I started talking about the t-statistic, which was a big. So I'm going to set the stage for this. The t-statistic was a big revolution in science. So we know the Gaussian distribution is after Gauss, and Gauss used a model that involved Gaussian variables or normal variables to study the distance to stars. Okay, but the model assumed that the variance was known, or that you have many observations, and that they were independent and they converged to the population limits. So student was able to find confidence intervals and put test hypothesis without assuming that the variance is known. So that was a big revolution in science, because whenever you have a parametric assumption, you might be wrong. The assumption is wrong. Then whatever you get out of that is not useful because it doesn't apply. So in the same way that the t-statistic was a revolution of science, there was a need for data-driven results, okay, in machine learning. Because if you use parametric assumptions, like knowing the variance, then you might be getting exactly the wrong result. But if you use the data in itself, then you're going to be more likely to be getting the right result. And so, and that's the property. So self-normalization martingales are basically stochastic processes in continuous time. You can write any stochastic process in continuous time or in discrete time over time as a martingale plus something else. And so by using that, one can devise algorithms that only depend on the data. You don't need to make assumptions on parametric assumptions. You only need to devise super martingale. So that's what people in machine learning are using. And that was a good boost to trying to get optimal algorithms. So the first optimal algorithms that I saw in bandits were self-normalized. Okay. Now, I mentioned the method of mixtures. So let me talk about that now. So in this section, we will use the method of mixtures to do an analysis of boundary crossing problems. This method was first introduced by Robinson Sigmund in a paper that was published maybe 2 years ago. So before most of you were born, but not me. So, and then refined by my co-author Lai. And this work was done at Columbia, where I come from. So maybe that's why I was hired, because I continued the tradition. Okay, now the law of iterated logarithm. If we have independent identically distributed variables and they're in sigma squared, and we take the sum, then the lim sup of the after value of the sum over the square root of 2 sigma squared log n is equal to 1 almost surely. That's the LIL. That's Kolmogorov's LIL. And again, we have a parametric assumption. The variance is known, sigma squared. So this is not, the LIL is not a self-normalized variable. And if you pick the wrong sigma, you don't get the right answer. So anyways, what is the law of iterated logarithm Kolmogorov's LIL telling us? So the bound, okay, so the lim sup of this without the absolute value is going to be equal to the square root of 2n log sigma squared log n, okay? And the lim inf is going to be minus 1. So if you have a random walk, what this is telling us is that the ratio, okay, this summation is going to be almost always, so these are simulations. It will always, almost all paths will be between plus or minus the square root of 2. In this case, we're having a random walk, plus or minus 1, so it's plus or minus the square root of log n. This is so most of the paths will have that property. Now, the way some machine learning algorithms are built is you're going to continue until the first time that you exceed this bound. And then you declare that you stop. And that's the optimal algorithm. Some of the optimal algorithms come from this. And then if you divide by the square root of n log n, then this is going to be in a band. Okay. So we want to thank Wikipedia, which is a very popular library resource. Now, so we want to extend this limit theorem to self-normalization, A of t over b, basically data-driven processes. And the assumption now is extended to assuming that this is a super martingale over t. Now, the mean doesn't have to be 1. It's just a constant. And in this case, we assume that it is less than or equal than 1 for lambda between 0 and lambda 0. And A of 0 equal to 1. Now, so we are going to prove a result, the LIL, on the basis of integrating with respect to a different density or different probability measure. And we are going to use the probability measure. So let's start by looking at this function, okay? So we assume that f of 0 to lambda 0 is bigger than 0. And without assuming an exact density, we're going to look at this function. So psi of u and b is equal to the integral of this df of lambda. Okay? Then this is a function of u and b. And when b is bigger than 0, so these are constants. When b is bigger than 0, this function is strictly increasing map on R plus, and this implies that the function c bigger than 0. Okay? If we fix c bigger than 0, then psi of u v is equal to 0. That's a unique solution, which we call beta of f of vc. So we have a unique solution, and moreover, somewhere you can verify that beta f of b comma c is a concave function, and it satisfies the problem. Where b is the supremum over y bigger than 0, where the integral from 0 to y df lambda is equal to 0. And the supremum is empty if this is equal to 0. Okay. So Robin and Sigmund call this these are called Robins and Sigmund boundaries. And the method of integrating with respect to density is called the method of mixtures. Now, when they were applying that method, they were thinking, or they were using it for situations where b was a number, not a random variable. So in this case, you see, I said this what you can have here is a random variable like a Brownian motion, and this is like the t for the Brownian motion. So bt minus lambda squared t squared over 2, that's a martingale, a super martingale, which has integral equal to less than or equal than 1. So the pseudo maximization allows you to replace this from being a constant or a fixed a boundary that is non-random to taking it to be random, and that's the key to the pseudo maximization. The idea is that now you're going to capture properties of a random process, and you can maximize and pseudo maximize. Find the pseudo maximum, which replaces the maximum in the case where b was fixed. Okay, so let's look at how this works. So here we are looking at the probability that AT, which is our process, like the martingale, bigger than G of PT, okay? Where G of PT is beta F of PT squared comma C. So it's like the inverse function. So the probability that AT bigger than G of PT for some T bigger than or equal than 0 equals to this probability. So we are now taking inverse on this side. So that this takes me to psi of AT. Yeah. Should I go back to the definition of psi? So psi is this integral. Okay. So we're looking at that integral being bigger than C. Now, I can then use Markov's inequality or Doo's inequality. And sometimes this is also due to Beal. When you have a super martingale, the inequality is due to Beal. If you have a sub martingale, it's due to Doo. So sometimes people confuse which one is which. But anyways, so let's call it Doo-Beal or Beal-Doo. And then, so we have this, the limit of t tends to infinity of this quantity by using Doo's inequality. And then Markov's inequality, or I guess Doo's inequality goes here. And Beal's inequality. And let me write the name. So in case some of the descendants of Beal are in the audience. So this is, I think he was a French probabilist. It sounds French.
He's too French in the room.
Oh, okay. So I'm glad that I am pointing this out. I speak French, but I don't count. Some French. Okay, so now, oops. So you can then integrate by Doo's inequality, you come to this, and then you take the limit as t tends to infinity, and this integral is bounded by 1. So it's less than or equal than 1 over c integral of df lambda, which is f of 0 lambda 0. So the fact that we do not have to have a density, but a finite measure, f of 0 lambda 0 is what allows you to deal with the log determinism. Because you want a measure that goes as flat as possible, close to the uniform measure, but the uniform measure, zero infinite interval. So you want to, so you are cutting it at some point. And so then this is the density that we use. Oops. This is the measure that we use, F, and it has, if we let log 2 to be the log, and log 3 the log, then we have for lambda delta bigger than 0 and lambda in 0 to a e to the minus c. So we had three different regimes where the canonical assumption applied. In this case, we need lambda between 0 and e to the minus c. And this is the density, or the measure that we use. Now, in example 4 of Robbins and Sigmund, for fixed c, beta f of b comma c is of this order. The square root of 2b log b plus 3/2 delta log b plus log c. Well, the good thing is they did the hard work because they already did this. As b tends to infinity. So this is the order. And so then with that choice of f, the probability that AT over G of BT equal to 0 is bounded by f of e to the minus c over c. Now, given that epsilon is bigger than 0, so given epsilon bigger than 0, we take c large enough so that this quantity is less than epsilon. Since epsilon can be arbitrarily small, and since for fixed c, eta f is of this order, the dominating value is square root of 2b log b. As b tends to infinity, then we can then say that the lim sup, the square root of at over the square root of bt squared log bt squared is less than 1. On the set where the limit as t tends to infinity of bt is equal to 1. Okay? So that's the law of the logarithm, self-normalized. And this is an important result because it is not using parametric assumptions. So it's a completely data-driven result. Any questions? And then if you have a super martingale, if we assume that this is a super martingale, then on the set that limit as t tends to infinity bt squared equal to infinity, then we have this. Okay, and an example, as I said before, was the case of conditional symmetric variables, which as a special case gives you the Cauchy variables. So this condition is satisfied. Okay, it's a super martingale. And then on the set where the sum of di squared is equal to plus infinity, the lim sup is this. So this allows you to get algorithms even if your variables have infinite meaning, which is very popular these days, heavy things. So it's a sharp extension of Kolmogorov's LIL without moment assumptions, which is also valid for questions. Any questions? You have been extremely quiet today. So these are the references. So the paper that I was referring to is by Yassin Abbasi Yadikori, David Pal, and Sabas Pebari. There's a very important book by Pebari and Latimore. Yeah, Latimore and Pebari. And so that's one place where our paper is cited. What is, they introduce our results. And then here is the another reference on exponential inequalities for self-normalized martingales. And my paper with Pang. This is the paper where the inequality, the super martingale for conditional symmetric variables was introduced. And this is the paper where the inequality that I showed is okay, is presented. So these are the references. This is sort of the beginning, the genesis. In the beginning, there was provinces. Okay, so anyways, thank you very much. Yes?
I have a quick question. What's the difference between pseudo maximization and method of predictions?
Okay, so pseudo maximization lies when the boundary is not random.
Oh.
In this case, we have a random boundary. That's what we call pseudo maximization because it's not a real maximization. You cannot maximize in that case. You have to pseudo maximize. Okay, and that's if you're doing data-driven results, you need to pseudo maximize as opposed to maximize because there's no real maximization. So that's a big question. Any other question?
Integral from 0 to some lambda naught. Okay?
Can you speak louder?
When you did the integral with respect to density, you did it from 0 to some lambda naught, some lambda constant.
Yes.
Why do we care about f decaying to 0? Because we only integrated up to some fixed value.
Oh, well, you see, we need to have a finite measure for these inequalities to apply. And so the LIL comes from taking the lambda 0 bigger than b. Thank you. Any other questions? Okay. Thank you.
Okay. Hopefully I don't take this thing away. Back to New York. So I'm Hao Ling Zhou. I'm a student of Victor Filipino, and I'm a fourth-year PhD student in Columbia University. So my topic, this is the last topic, as Siva introduced. This is I will be talking about two applications of the lectures that Victor gave to you. One application on Boolean optimization. This is an application of the decoupling inequalities. And the second part, naturally, is an application of the self-normalized process. Shall I stand in the middle?
Yeah.
Okay. So the second is application of the self-normalized processes on linear stochastic methods. So in the first section, we introduced work by Martingale and Sviridenko in 2018. They used a type decoupling inequality, which is an extension of those decoupling inequalities that Victor introduced in the previous lectures. I think it's in lecture 2. And they use this decoupling inequality to bound the integrality gap of a certain type of program, Boolean optimization. And they used this linear program approximation by just relaxing the original Boolean optimization to a linear program. And they can use this decoupling inequality to bound the integrality gap between these two problems. Okay, so let's start from a leading example of load balancing. Assume we have m jobs, tasks, m jobs, and apply to n machines, and we want to minimize the total energy cost. So we will have a matrix of variables. The Yij would be 1 if the task I is assigned to machine J, and it will be 0 otherwise. So naturally, the summation of all J of Yij should equal to 1. Actually, only one of them is 1 and the other are 0, because a task can only be assigned to one of the machines. And the Dij's are known model parameters, parameters of the system. It's the processing time if task I is assigned to machine J. And the total processing time of machine J is just summation of all i's, Dij times Yij. Let's call it Wj. And the energy cost, we assume it to be a convex increasing function. For example, a power of the Wj processing time. And to be more precise, we want this Q to be greater than 1. So that's something called diseconomy. That is to say, the machine is getting more and more tired if you assign more tasks to it. The marginal cost, the marginal energy cost of the machine is increasing. So the total cost is the summation of all J of the energy cost. Then the problem is formulated as such. Minimum of all the Y's, summation of all the machine J's, of something to the power of Q. This something is the processing time of the machine J. It is summation from I to n, Dij times Y. Under the constraint that the Yij summation from 1 to n should be 1, and the Yij's are binary. The second line is also equivalent to say that only one of the Yij's are 1, and all the others are 0 for each I. Okay, so we now come to the general problem that their paper analyzed. They consider the following class of Boolean nonlinear programs. Minimum for all, minimum of this summation where this power of Q is replaced by a more general convex function Fj that is allowed to change among the different machines. Again, summation of the DIJ We dropped a subscript. Previously it was YIJ, but now it is YI. But this difference is not substantial. In fact, you can write this load balancing problem in this form with an additional subscript, but that's a trivial thing. We also want to introduce another general notation of the linear constraints. That's to say, we want this y to reside in some polytope that represents a finite set of linear inequality constraints. The yi's are Boolean. The dij's are known parameters of system that are non-negative, and the fj's are non-decreasing convex cost functions. Okay, so in order to proceed, they applied this change of variable thing so that they can relax this Boolean problem to a linear problem. They changed this variable y's to a variable z's, where y's are Boolean vectors, right? So if you know the indices, the locations of ones of it, you know y. That thing I call sy. Sy are the locations of ones in y. And then we introduce an indicator function over all possible subsets of 1 to n, where this indicator function zs is 1 if and only if the input s equals the subset sy, the locations of 1 to y. And otherwise ds is 0 for other subsets. In that case, we can transform the target function fj of the summation of dij to a summation we add additional summation over all possible subsets s. Recall that zs is 1 if and only if this s is sy, and otherwise 0. So this summation is only consists only one term, because the other terms are 0. So in this way, the original problem we call IP, integral program, is equivalent to the following one. So we add another layer of summation over all s, and then summation over all j machines. The zs is the indicator function over all subsets of 1 to n. The zs is also Boolean. The summation is 1. Actually, only one of them is 1. The yi is a summation of zs such that I is in s. And the vector y retrieved from zs. So this line is just changing this zs back to y. You can verify it yourself. The y should also satisfy the polytope, the other linear constraints. Yes.
We had yij to start with.
Oh, right. So I dropped this subscript j for a general problem because let me see how I can explain that. So that one is the first one is a leading example, but then this is the general problem. We can always change this summation of I to a summation of multiple indices. So that by adding another subscript, this load balancing example is a special case of this.
How is it a special case?
Okay.
Because to start with, I had m times n y variables. Now I only have n.
Yes. Okay. So suppose I write it in that way. So this is the load balancing. And the summation is from I to n. Summation of I from 1 to n, dij, yij. And I say that this is the general form, but I dropped one subscript. How come that this one is a special case of that one? Well, I can define this I let's call this I prime. It consists of a multiple index. It is actually ing. And naturally, you will have y of I prime. This I prime is a double index. And then dij, let's say j prime, where this has three indices and some of them are zero. So by raising the dimension, one is a special case of this. So where are we now? Yeah, here. This is a equivalent to the original problem. So far, I haven't done anything. And then we relax this one. This is equivalent to I. How do I relax it? First of all, I allow this ZS to be able to change for different machine J. So that we now have ZJX. And secondly, we allow this ZJS to take non-integer values in the interval 0 and 1. And all the other constraints are basically the same. It's just that the definition of y should be changed as yi should be equal to summation of s such as I in s of ZJS. The last line also implies another constraint is that, see that the left-hand side is yi, but the right-hand side also depends on j. So the last line also requires that this summation for all j are the same, and this summation is equal to yi. And this vector y should satisfy all the other linear constraints represented by this polytope B. So this is the relaxation. More precisely, how is this a relaxation? Well, first of all, their target functions are the same, exactly the same. They didn't change the target function. And second of all, this thing is equivalent to the previous IP, transform of IP, this thing, plus two additional constraints. First of all, the ZJS should be Boolean, and second of all, the ZJS should be equal. If you add the two constraints, then the two things are the same. So this LP is indeed a relaxation of IP, and this LP is basically a linear program, thus easier to solve. I believe you all know better than me the solutions of linear programs, the fast solutions. The only problem is that the solution of this LP linear program are non-integers. They are values between 0 and 1. So how to get integer values back? Well, the first thing you can think of is just II Bernoulli draws, because this yi stars the solution of the LP. Sorry, there should be a star. Should be a tilde here. The blue things are between 0 and 1, and so they serve as good probabilities. You can draw ID Bernoulli's, and you get a Boolean vector yi hat. Let's call yi hat. And then the yi hat, they propose this is a near optimal solution of the original. The question is how near it is. How far is this y hat the Bernoulli draws are from the optimal, right? So this is where the decoupling equality kicks in. Let's first give you the theory. So suppose the model parameters dij are strictly positive. Well, this is not too restricted because you can assume they are non-negative, but it involves some other treatment of the zero elements, making the notations clear, but the essence are the same. So the first part of this theorem says that if y tilde and z is a feasible solution in all the constraint of the LP, the relaxed program, and we let the y to be Bernoulli draws ID, then the expected loss of this Bernoulli vector y hat is bounded by something. Look like this. And this something is if you subtract this A of fj out by taking a supremum of all j's, and you take this A of j out, you said that this thing would be the loss of the LP, the transformed program. Where this what is this A thing? This A thing is defined as such: a supremum about t, positive t, expected value of f of tp divided by f of t, where this p is a Poisson one variable that is independent from everything else. I will come back to this later. The second part of this theorem says that, well, if y to the star and the star is a 1 plus epsilon approximate optimal solution to the linear program, then you get the Boolean vector yi hat using Bernoulli draws. You will have that these Bernoulli draws, the expected loss of these Bernoulli draws is less than 1 plus epsilon times max j of these A functions times L of IP, where this L is the optimum cost of the original problem, which means that those Bernoulli draws y hat is a 1 plus epsilon times max of j A of j suboptimal solution of IP. This max of j A of j serves as a inflation of the loss. So how large is this inflation? Here's an example. So if the fj's are polynomials, as in the first example, xq for some q greater than 1, then this A of fj is just the qth moment of a Poisson one variable. And it is called the Bell numbers, as some of you might know. So this is a sequence of Bell numbers. When q is 1, it is 1. When q is 2, it is 2. And then 5, and then 15, then 52. Usually we don't encounter power of 5 in applications. So suppose q is 2, the quadratic loss, then this inflation is 2. So back to this. If you can find a 1 plus epsilon approximate optimal solution to the linear program, then the y hat the Bernoulli draws is a 2 plus 2 epsilon suboptimal solution of your. So this is the main conclusion of that paper. Let's quickly go to the proof. So this is the decoupling inequality that they invented, and this is a extension to what Victor has introduced in previous lectures. It has the same flavor. It is a bound of an expectation of a convex function of a summation of things, where this things, the x are possibly dependent sequence, where this yi's are independent, but the yi's are complete decoupling of xi, meaning that each yi will have the same marginal distribution as each xi's, but the yi's are independent between each other. So this has the same flavor as those decoupling inequalities that Victor introduced in previous lectures, except that they have another variable p here. It is a Poisson variable independent from everything else, inserted into the phi function. And the second part of this theorem is just the sharpness, meaning that if you allow for an margin one minus epsilon and flip the direction of the inequality, then you can find special examples of y and I such that this thing holds. Which means that this inequality 6 can be arbitrarily close for specific choices of y's and x's, meaning that the thing is sharp. So a natural corollary is this thing. It's basically somehow extracting this p outside of everything else. How do we do this? We use this definition of A of phi, supreme of t. Let Sn denote the summation of xi's. Xi's are the possibly dependent sequence. By theorem 2, the previous one, expectation of phi of summation yi, the complete decoupling, is less than this thing is just the right hand side of this. I just wrote summation of xi to be Sn, which equals, by Tower rule, we insert another conditional over all the Sn. By definition of A phi, since this Sn is conditioned upon, we can think of this in Sn as t. So this is E of phi of Tp. And this A phi is the supremum of E phi Tp divided by phi of t. So this thing is less than a of phi times phi of t, where t is Sn. So inserting this back, this thing is less than a of phi times phi of Sn. Sn is the t. And then we insert it back, we have this final result. So we kind of extracted this p outside and turned it to a phi. And a phi is, think of the Bell numbers when this phi is the powers. Okay, so let's give a sketch of proof. Let's give a sketch of proof of the main theorem, the near optimal solutions things. So suppose this is the first part of theorem. Just put it here so that you don't forget it. The yi hats are the Bernoulli draws, and then we want to prove this thing. It is first of all, the summation over j can be taken outside. So we only need to analyze this thing for a specific j, or for each fixed j. The first thing is to compare it with the corollary 3, the last corollary I get, with the capital Y hat to be dij yi hat. And then we need to find the xi associated with that yi. The yi's are, dij is deterministic. Y hats are IID Bernoulli. So yi is the complete decoupling sequence, decoupled sequence. The question is to find xi, the possibly dependent sequence that their marginals are the same. Now, how do we do this? I will skip the details because we don't have enough time. Basically, xi's are defined as such, where xi equals to dij if and only if I is in a random subset T, where this random subset T has a distribution ZJS. So ZJS, the solution ZJS can be regarded as probability distributions of a random subset S, where T is a instance of it, so that we can define xi to be dij if I is in T and 0 otherwise. In this way, you can verify that xi indeed have the same marginals as ys. And then using the corollary, this one, using this corollary, with yi being this one, dij y hat, and xi being the thing I blurred away, we will have the final line, which is exactly what we want to prove. So this is how they use the decoupling inequality. And the second part is the approximate optimality. You just insert everything into the linear program. The left-hand side is by part 1 less than this thing. And then if you extract all the a of fj's by a maximum of j, you can exchange the summation of j and a of fj. And then this summation is exactly the optimal solution of the linear program, LP. And by assumption, this ZJS star is a 1 plus epsilon optimal solution of the LP. So it is less than 1 plus epsilon times max JFG of the loss of IP. Okay, let's not focus too much on the proof of that. Let's summarize this a little bit. So in that paper, the authors, Makarevchev and Svidenko, studied a certain class of problems called IP. And they used the change of variables. They changed the yi's to the variables ZJS and relaxed it to a linear programming. And the linear programming is easy to solve. They developed a sharp decoupling inequality, that one involving the Poisson variable, which is an extension to those introduced by Victor previously. And finally, the decoupling inequality plays a central role in bounding the integrality gap, the small the theorem involving the 1 plus epsilon near optimal solution. So this is the takeaway of the first bit. So far, is there any questions? Yes, please.
Is it really easy to solve this LP because it's of exponential size?
Yes. Well, I'm not an expert of engineering as you people do, so I can. The authors claim that this problem is easy to solve. Go back to the.
Yeah, but I'm just confirming it's of exponential size. So it involves the subset S.
Yes, it is exponential size. Yes. Yes, please.
Maybe I missed it, but can you give some idea of why the Poisson distribution is coming up in the decoupling inequality? In your theorem, on the decoupling theorem, you have a Poisson random variable on the right.
Yes.
So where is that coming from?
The way, so what they do is they take the random variables and they atomize them. That is to say, they divide it into many variables, and there's a Poisson number of variables that can be reconstructed variables. Okay, so that's where it comes.
Thank you. Any more questions? Okay. So in the next section, I will introduce another work on linear stochastic bandits. And it is an application of the self-normalization concentrations. This work is written by Abbasi Khoury, Hao, and Chepeswati in 2011. They study the linear stochastic bandits. Now, I don't claim that this method is anyway cutting edge, because given that it is more than 10 years ago, I guess it is stone age to you guys now, but it's still relatively new to us probabilists. So this here is a quote of their abstract. It's the same as the one Victor just showed. The key is to find a smaller confidence sets, and then to construct the confidence sets, they used the novel tail inequality for vector value martingales, which is that inequality Victor introduced for vector value martingales. Okay, so here is the problem. Suppose you're a player, a gambler, and you're faced with the slot machines. At each round T, you invest a vector xt, which is xt1 through xtd to each of the slot machines. And this vector xt resides in the d-dimensional probabilistic simplex. That is, each of the elements are non-negative and they sum to 1. For each of the machines, okay, for the kth machine, the return is xdk times a theta star of k. This is the intrinsic rate of return for the kth machine, this theta star. It is unknown to the player. Then the total return is then the summation of all these linear terms plus a stochastic noise, eta t. So the total return yt, if you write it in vector form, it is xt transpose theta star plus eta t. The goal is to sequentially choose the xt in the probabilistic simplex at each round t to maximize the total gain, excluding the noise eta t, because later I will show you, later I will assume that eta t is conditionally zero mean. So we want to maximize the total gain, the linear gains. Let's define the filtration to be the player's knowledge right after the round T. So right after round T, what is known to the players? First of all of his or her previous bets, XTs, and second, all the eta Ts. the noises, which is the only stochastic part of the return. At the beginning of round t+1, the player decides this new bet xt+1 based on the current information. We also assume, like I said, this eta t is conditionally zero mean, which means that this eta t is a martingale difference sequence. The summation of eta t is a martingale. And finally, we assume this theta star, this unknown parameter vector, has bounded L2 norm, bounded by some known k. The authors considered the following algorithm called optimism in the face of uncertainty, OFU. It maintains a confidence set Ct of the theta star. And at each round t, the player chooses a pair of xt and the best guess of theta. Let's call it theta t2, to be the argmax of the linear return. Constraint over x being a probability vector, and theta is in the newest confidence set. Then the player receives the new reward, yt. And then, based on this new information, the player updates the confidence set ct. So the key is to maintain this, construct and maintain this sequence of confidence set ct of the star using the current information. The self-normalization is a powerful tool for this, because the self-normalization, think of the t-statistic, right, and the t-test. They have this statistic t, and they know the concentration of t. Actually, they know the exact distribution of t to be the t distribution. And they use this concentration to construct confidence intervals. Similarly, we will use a self-normalized statistic that I will later show you, and then we will have a concentration for it. So using that, we will have the confidence set. Actually, the confidence set is here, this one. It is a ellipsoid. So first of all, we estimate this theta using bridge regression, where this matrix X is all the investment vectors up to time t. And I'm dropping the subscript t here because otherwise it would be kind of long and ugly in the next few slides. And the y is the return vector up to t. Lambda is a arbitrarily chosen regularizing exponent. And I is an identity matrix. This VT is exactly the bridge formula, right? So let's define VT bar to be this matrix, X transpose X plus lambda I. And we denote the VT bar norm to be the norm induced by VT bar, which is for a vector X, the VT bar norm of it is the square root of X transpose VT bar X. It is the matrix induced norm. This term says that the confidence set is defined as such. It is a ellipsoid, because if VT bar is identity matrix, then this thing is a sphere, no, a ball in RD. But because VT bar is not identity, this thing is an ellipsoid in RD. So you can see that the square root of the determinant over determinant, this thing showed up in the first section today. Okay. Okay. So this is the concentration that I mentioned in order to construct this confidence set. Let eta t be a real value process, which is the noise process, adapted, and conditionally R sub Gaussian for some R, which means that it's moment general function, conditional ft minus 1 is bounded by this function. This is the definition of sub Gaussian. Let xt be a RD valued process such that xt is ft minus 1 measurable. Xt is just the investment vector. Assume V is a deterministic matrix. Later we will use lambda I as this V. But this lemma is valid for any positive definite matrix V. For any positive non-negative t, we define Vt bar to be that thing, and St to be summation of eta times xs, summed up to the current time t. Then for all delta, with probability at least 1 minus delta, this is concentration. This inequality holds for all t. So this is more or less a uniform concentration. I will postpone this proof of this concentration after everything else if I have time. But for now, let's assume that this lemma is proven. So you know the concentration. This is analogous to the concentration of the t-statistic. And then how do you construct a confidence interval based on the concentration? So I will give you the proof of the main theorem, the confidence set, using this lemma, this concentration of ST transpose VT inverse ST. So how do you do this? For the ridge estimator theta star, these are all equalities. These are the features of the ridge estimator. So the ridge estimator is this: x transpose x plus lambda I inverse x transpose y minus the true theta star. I insert the definition of y, which is x theta plus eta, just like you did in the linear regressions, minus theta again. This thing is defined as Vt bar. So this is Vt bar. So x transpose x is Vt minus lambda I. So this is x transpose x, theta star. This is this term, right? And this is second term, minus theta star. Notice that Vt inverse times Vt is identity. So the first term is theta star. It is cancelled with last minus theta. What is left, anyway, is this thing. So the Vt bar norm of theta t hat minus theta star, which is defined as such, is this. We insert this expression into this, we get the second line. And then the second line is the Vt bar inverse norm of this vector, x transpose eta minus lambda theta. And the x transpose theta is exactly St, as we define it. So we get the third line. This thing is exactly the Vt bar inverse norm of St minus lambda theta. By the triangular inequality, we just bound the Vt bar inverse norm of these two components separately. Luckily, the first part is exactly the previous lemma that I pretended we have already proven. And we will prove it if we have time. Based on the cloud, I don't think we have time for that. But assume it is proven, then that lemma, let me roll back.
I want to mention,
Yes.
that looks like the canonical assumption.
Which one?
The bound on the expectation.
Theorem statement.
Yeah,
This
that,
one?
no. For every lambda figure in our expected e to the lambda.
Yes, absolutely. This thing will appear in the proof as a key step in establishing the canonical assumption. The canonical assumption is related to, as you may recall, the super martingales. And this condition would be used to verify that something is a super martingale. Okay, we go back to this. Okay, we're bounding the two terms, these two terms. The first term is already bounded by that lemma. The right-hand side is r square root of big thing. On the other hand, the Vt bar inverse norm of lambda theta star is bounded by its L2 norm. Because this Vt bar inverse, this Vt bar has a ridge component, lambda I in it, so its curvature is greater than lambda. So its inverse is bounded by lambda inverse. So the VT bar inverse norm is bounded by the L2 norm. And we assume this L2 norm of this true parameter is bounded by K. So the second term is bounded by square root of lambda times K. If we add these two right-hand side bounds, we will get the main thing, exactly the addition of the two bounds. And this is an elliptoid. This is confidence. So let me quickly summarize things. First of all, this paper by Abbasi Yakdori et al. Studied the linear stochastic bandit problem using the OFU algorithm. Okay, the L in the last stands for linear stochastic bandit, but I tend to delete this L because it sounds like awful. And then constructing a confidence set of theta star plays a central role in this awful algorithm. It's not awful, it's brilliant. The concentration of self-normalized processes are powerful tools in constructing confidence sets. The concentration is again this thing, which we pretended that we improved. And pseudo-maximization is an important method in improving such concentrations. I don't have time to show this, but it is exactly related to the concentration that Victor showed in the first section, the matrix and vector form. Okay, so here are the references: the Abbasi paper, the Victor's 1990 and 2009, and also the Martingale paper on the load balancing problem. So let me take some questions. Okay, so there's no questions. Let me quickly, so there are 5 minutes, 7 minutes. Let me quickly go over the proof of that concentration. ST transpose VT bar inverse ST, that thing. So according to the paper, this is a quotation. That theorem could also be derived from theorem 14.7 of the Pena 2009. This is the paper that Victor wrote with Lai and Shao, right?
That's the book. The paper appeared in 2009 as well, and it's with Class and Lai.
Oh, right.
So, but that's the book. So
Yeah.
Yeah, they read the book, not the paper.
Yeah, they read the book, and this lemma is theorem 14.7 in the book, and this thing was introduced by Victor in the first section today. So let's review this lemma. Let a random vector A and a symmetric positive definite random matrix C satisfy the canonical assumption. The expectation of exponential this thing less than 1 for all lambda. Let V be any positive definite non-random matrix. This V later would be this lambda times identity. Then this thing holds. The expectation of that thing is less than 1. And since this is a bound of the expectations, we will use the trick that you have already been familiar with, the Markov inequality. We raise things to the power to the exponential, and we use Markov inequality. This thing appears in the right-hand side, so what's left is 1 over delta. Something like that. So let me put the lemma in the above this page, in case you forget. The goal is to prove a uniform concentration for ST transpose VT inverse ST. We compared this with the form of this lemma. We let C to be X transpose X. We let A to be ST. We let this V, deterministic V, to be lambda I. The proof uses this lemma and plus a stopping time argument that I will show later. This stopping time argument will prove the uniformity of this concentration. We claim that if we define VT to be X transpose X, okay, so here is a abuse of the notation here. I'm sorry. So X transpose X is both C in this inequality and VT in the following mathematics. So we claim that S tau and V tau for any stopping time tau satisfy the canonical assumption, which is expectation of this thing is less than 1 for all lambda. And this is proven using the fact that if you define the inner side of this expectation to be empty of lambda, this thing is a super martingale. You can verify it yourself because I don't have time using the sub-Gaussianity of ATAS and perhaps 2 or 3 lines of mathematics. This thing is a sub-martingale and this initial value is 1. So the canonical assumption is met. A detail is that since this is a super martingale, it almost surely has a limit, so that S tau and V tau are well defined, almost surely. By the lemma, this is just the result of the lemma. This expectation is less than 1 for S tau and V tau. Then we use the classical arguments, raise it to a power and use Markov inequality. We show that this concentration is less than delta, 1 over delta. So the probability is less than delta. And this is concentration for S tau and V tau. And how do we go from this concentration of S tau and V tau to a uniform concentration of ST and VT? We let tau to be a specific stopping time. We let tau to be the first time that the inequality is broken, the boundary crossing time. The first time that this inequality is broken. With a convention that infinity of a null set is infinite. We have that the probability of this uniform bound, which is there exists a t such that this boundary is crossed, is equals to the probability that tau is less than infinity, because tau is defined as the boundary crossing time. And then we add another condition to this probability. The condition is S tau transpose V tau, S tau is greater than or equal to that. Because under the event that tau is less than infinite, we know that this boundary crossing happens before infinity. Then we can insert tau to be t, and this larger than sign becomes larger than or equal to, and without changing the probability. And we can delete the tau less than infinity condition to get a upper bound of that thing. And this thing is exactly the concentration we get for S tau and V tau is bounded by delta. So we get a uniform concentration for ST and VT. So this is a classical trick we use to prove uniformities using this boundary crossing stopping time argument. So this is it. Is there any questions? Okay, then, so this is the last of my page. Let's go back to the references. And thank you so much.